So the next speaker is Claudio Mazzoli. Claudio obtained his PhD from Parma University in Italy, and then spent several years, 7 years precisely, at ESRM on hard X-ray magnetic scattering beamline. At that same time, he was also had an invited professorship at University of Nantes in France, and then he spent 4 years at the Politecnico di Milano. Okay. Yeah. Focusing on soft resonant inelastic and hard resonant elastic X-ray scattering, and then for the last several years, he is a principal scientist at NSLS-II for the CSX beamline, and he's the lead beamline scientist at the Coherent soft X-ray beamline. So he's gonna talk about a coherent soft X-ray scattering view on electron behavior in correlated materials. So with that, Claudio.
Thank you very much. Thank you very much for a kind introduction. Went wide back by now. My other career. Anyway, so this is the official talk, but in reality, oops, it works. Yes. I will present few cases of partially coherent soft X-ray scattering views on electronic behavior and correlated materials. As we have just heard, NSLS-II, the source of BNL, is not fully coherent. So that's the reason why the title has to be slightly changed indeed. So the outline is very simple. It is just electron correlation in materials and why we are interested in it. Use of coherence available at modern synchrotrons, although partially we can do quite a bit out of it. There are a few examples that I would love to present, and then pinpoint some advanced contribution and new concepts that I believe were coming out before drawing conclusion and future perspectives. So this was obviously the work that went through many years, and so there are many people that have to be thanked and acknowledged, together with obviously the organizers that gave me this opportunity to present our work. I hope I didn't forget anybody here. So why we are interested? Let's say we are interested in electronic behavior in matter, and the reason is that we all know that at microscopic scales is quantum mechanics that describes everything, but at our scale of time, energy, length is in reality classical physics. Sometimes there are some phenomena that are able to go through the mesoscale without being too much perturbed, and so preserving some of their quantum nature, and this is typically referred to with emergence, right? And these are some examples, but anyway, whatever you looked at, they are all related with electronic behaviors in space and time. So it is particularly important, even because most of our life is actually lived around electronic behavior. Apart from our mass and for nuclear reaction, everything else is essentially electronic, right? So storing of energy, information, calculation, anything is done, even the colors, everything, right, is done through at a certain moment. It involves electrons in some forms. So it is particularly important, and Tokura, way back almost 10 years ago, intercepted the double nature under which this came out with, let's say, the fractionalization part and the superconductivity that were the two originally, the two communities that gave rise to this kind of concepts and evolution down to our nowadays, where you can recognize at least some of the trends. Indeed, obviously, it's not only a matter of concepts, it's very important for advanced application. I just picked up two just because, but it's storage and calculation through magnetism, magnetic quasi-particle. If you are my age, you saw the transition between, let's say, traditional hard disks and the magnetoresistive based one that densified the information a lot. And then we went other orders of magnitude on just because we changed technologies, not necessarily magnetic, but it gave advantages and disadvantages, obviously, but indeed made the progress, right, to run around us and gave us a lot of options and possibilities. And now everything is about quantum information in general, computation supremacy. This was done a couple of years ago, and it already looks like more or less dinosauric approach, right? Because everything is going so fast in the scale that every other day we have the doubling or the tripling of qubits that are told at least to interact correctly, although for the moment, right, not a lot as we that way. So there's a lot of application, and very important one, right, at the forefront of what we can do, and we hope at least to be able to say something. So let's try to tell more clearly what are we interested in doing. We have a goal. We want to investigate and model nature, which is equivalent to say we want to be scientists, right? Our focus is condensed matter physics, in particular hard condensed matter physics, electronic properties in material. We can identify three tasks. One is fundamental origin, so it's scientific in itself. We want to understand electronic behavior, structure, dynamics, correlation, whatever you want. And there is an engineering one, an applied one, right? We want to control and use electron our willing, possibly to give rise to new devices, new materials, new applications. And then there is one technical that is to make this to be realized, actually we need the tools, right? So it's non-trivial to try to retrieve microscopic information. When microscopic means at the nanoscale if you want, but it's right at the level of the interaction, right? We should say like this. And we need to do it in different ways compared to the past to actually access information above what was done in the past. How can we do? Okay, we want to target electrons, charged particles, typically moving. So obviously radiation is the natural way of thinking about as a probe. We want to study, as we said, structure, correlations, right? So we need to exchange momentum. So X-rays is more or less where we immediately have to deal with. As you know, most of the electrons in atoms are essentially there just to create, to fill the space, more or less, right? And it's only the skin around, right? The last shell that is the one that is keeping everything together because it's unshaking with their neighbors somehow. And is bringing about all the properties that thermodynamic or quantum that we're interested in. So we need to target those electrons specifically. So we need to have resonant X-rays. And then we will see that to extract, as we heard already, right, space and time behavior, sharp characteristics out of it, we need coherence. So to do this and to exploit it to the maximum of its possibilities, we have to use scattering and spectroscopy together. And the way in which we do it is through resonant elastic X-ray scattering or diffraction, which is a photon in, photon out process that is identical to diffraction, except that the intensity of the detector, it writes with a modified atomic scattering factor. So this normally in normal diffraction is a quantity, a complex quantity that depends only on the modulus of phi, the exchange momentum that appears here in the phase part. Instead, if you're at resonance, it depends on the details of the incoming and outcoming light in the sense that it depends on the polarization and their momentum. And so it's a tensor. That's the reason why if you take the Bible of the crystallography, which is the crystallographic tables, about in the second page, it says everything you read here is only true far from any absorption edge. Not because you cannot perform diffraction around absorption edges, is what we do, but because there is a modification in the laws, right? So it's not anymore exactly what is written there. It's actually a richness that we can use to extract more information. The important part is that there are clever people that calculated everything for us. And second order perturbation theory of quantum mechanics allows us to calculate these elements, provided all the complexities indeed encoded here, that you can calculate what the intermediate states are. What you're doing is you take a photon, you shine it on an ion. At that point, you can consider only one single ion. You don't care. Its cartoon picture is here. You target the resonance of a core electron. This makes it ejected, not out of the ions, but at least if it has enough energy, just above the Fermi level. It cannot be below because it's full, obviously. So there is no receptive levels for it. So it has to be above. That's the reason why you have this integral that goes from Fermi level to the infinity at the limit. So you photopromote the electron here, and in the radiative process is not the only one. You only care about the radiative one. The radiative process, that's the reason why it's second order perturbation theory, by the way. So the radiative process that brings one of the electron down to fill the hole that you left behind you emits the photons. And if you get that photon, if you collect that photons, the intensity, polarization, and direction tells you about the symmetry of what the photon interaction has witnessed inside the matter. And this brings out microscopic information on the shape, direction, intensity, and so on and so forth of the electronic orbitals that were seen. Everything I said is exactly identical to what is written here in this numerator, although a little bit more complex. You have to notice that initial state and final state in general are different. As I said, any other electrons descending here. So you are dealing with elastic scattering. If and only if the initial and final state are identical. Obviously, photons do everything that is symmetry allowed, so you will have all the conditions coming out. And you can have elastic and inelastic. If you use Bragg, if you're allowed to use Bragg, then the Bragg condition enhances enormously the elastic part, and everything else is essentially a background, so you may be able to say something, but you have to be attentive. It's not always the case, and we have to be careful. We have one detail more now. We want to plug in coherence. We heard the fantastic presentation of Antoine before. So luckily I don't have to say a lot. I like to use this sketch because I find it extremely telling. If you don't control, if you only poorly control your wavefront, where the average distance between peak and valleys is fixed, lambda, right? You have one way of accessing microscopic information. Clever people before us showed that you can encode in geometrical, in particular in this anchor, right? In geometrical measurements, the ratio between two microscopic quantities. If you know lambda, you extract the lattice spacing of your crystals, right? This is a typical basic powder diffraction experiment, and we all know the result brings. Now, if you plug in beam coherence, so you do better in controlling your wavefront somehow, although it's a little confusing, and maybe we will talk about a tiny little bit more after. What you can get is that what was a diffuse ring before gets in focus, right? And you see that there are details appearing here. Those details that are called speckled or speckled pattern are indeed encoding the Fourier transform of the distribution of the scattering object inside your target. So it's an incredible amount of information. This is exactly what Antoine was referring before, in the sense of exploiting its resource, and in the difficulty, for example, of making all the calculation and taking care of everything. All right. We all have experience of this. There's nothing really special in reality, for two reasons. First, because any source can be made coherent. It's sufficient to collimate properly and filter properly the energy, and you get a coherent source. The problem is without many photons left, right? One photon is fully coherent. But you cannot, unfortunately, do a lot with out of it, certainly not to explore electronic properties in materials. So there's a challenge. The other is that we have sources already realized since years that are fully coherent and are lasers. This is a reflection of a laser out of an imperfect surface, and you see immediately all the spectrum. It's actually our alignment laser on the beam. So that reminds us that we are coherent. And you see all the speckles, right? And it's the distribution. If you imagine you can draw an envelope around, and it's more or less a Gaussian beam. But the distribution of intensity pixel by pixel varies a lot. This is what speckles means. And it is due to the fact that it's reflected out an imperfect surface. And so by Fourier, if we were able, Xiaojing will tell us how to do, if we were able to Fourier transform back the information here, we would know what the imperfection on the surface convoluted with the source emitting this coherent laser would be. In reality, light coherence is a long story, as partially Antoine touched based on. And it started pretty soon, as much as we understood, clever people understood, that light has an oscillatory behavior, right? For obvious reasons. Also because it's one of the ways in which you can somehow parameterize what you're looking at as a source, essentially. And indeed, there are two fundamental sides. One is the time or longitudinal part, that's to deal with how monochromatic is your wavelength, right? Your light. And it's all encoded here. This is typically the resolving power of monochromator or equivalent device. And the other, as we already heard, is the space or transversal part, which is the solid angle under which you look at the source, right? You forget about everything in between. We saw that there are effects indeed. One of the questions was related with this. But in first approximation, you remove all the optics, you look at the source and you say, how large is my angle under which I can see the source? Right? And this is exactly bringing back how accommodating you are compared to the phase that is coming out of different parts of the source, as Antoine has described very well. Now, it is important to insist a little bit on the decoherence, right? It's difficult to obtain coherence. We said, no, it's difficult to obtain a lot of photons coherent, because to obtain coherence in principle is very easy. One photon is coherent. The problem is that when the coherence is there, it's difficult to remove for the same reason. So if you generate something that is coherent, it's difficult. You saw it with a laser pointer, right? You make the reflection out of an imperfect surface, you crumble the wavefront. It's not that you destroy the coherence. The coherence is there. It's not flat anymore, but it's there. The point is that to destroy coherent effectively, you have to use the property of light. What is the fundamental property of light? It is of light. It is a transversal spatio-temporal wave. You have to mix space and time. If you mix space and time, you destroy coherence. So it's exactly the question of before. If you have an optics that is vibrating, is the way in which you destroy coherence. Is it true? No, it's not true, but it's true on average. So every single experiment has a detector, our eyes, whatever it is, and you have a sampling timing that defines a basic time structure in your experiment. If everything is faster than that sampling time, on average, you don't see coherence because you have speckles, but they move faster than what you can appreciate. And so on average, you see only the envelope of it. Goodbye to the speckles. Okay? That's the only way that we know to remove coherence. If we understand well this part, it's already quite important. So this comes with the important concept that times and space are mixed. So there is a mixing concept that is intrinsic to the coherence in the fact that if it's there, it means that they are properly separated somehow, okay? And not improperly mixed, if you prefer. Indeed, the only way to destroy is either to allow that this guy depend on time or to allow that guy depends on time. So if you have a mirror that is vibrating or a mono that is vibrating, you will see very soon that you destroy the coherence very effectively. I can tell you that it took quite a bit on the beam to resolve the problems that were destroying our coherence, unfortunately. So the important concept, diffraction limited synchrotron sources are not lasers. They have, everybody squeezes down the electron beam as much as possible. You resolve one of the two parts. You see I left it here to remember that there are two parts because of the nature of the light, right? So we solve this part, we do not solve this part. So we still need the monochromaton. So it's important, the stability, because at the bare minimum, the monochromaton has to be somewhere. So if it's not stable, thank you very much, goodbye. And then otherwise, we can try to use modes as a kind of description. Antoine quickly said something about, right? But it's not obviously, it's a mitigation. Okay. There's something else that we need to remember when we talk about coherence for the use of experiments. So we can only measure photons that are coming out of matter, and we want to, and we hope that the encoding of the relevant information for us, that is the microscopic interaction with matter, is measurable, right? But in reality, obviously, as any technique, you have constraints that are windows in time, space, energy, momentum, call it as you want. And in general, given that coherence starts at the source and it's measured at the detector, everything that is in between may have an impact, like a vibrating mirror, monochromaton, the sample, maybe. So we need to be sure that everything else is okay before trying to say, what we see comes from the sample, because it's not so obvious. It may appear obvious, but it has been source of quite a bit of errors in the past. So we need coherence kits, essentially. How can we do it? Well, although partially coherent, we can do something out of the beam. This is the plan of our beamline. We have branch beamline. In reality, are two side-by-side sister beamlines fed by two independent ondulators. It's an EPU, in our case, from 200 to 2000 electron volt with full polarization control. That's the cartoon picture. These are the numbers. And you see the elements are more or less these ones. And it's a very small number of elements, exactly because the least the number of elements, the better you preserve your coherence. Because if you have figure of errors, as we said, the beam tends to deviate from the natural propagation. And so any aperture that you have after will lose photons. And if you have vibration, you mix space and time, and so you lose context, right? You lose coherence. So 3 elements, actually 4, because the monochromaton obviously has 2, but essentially 3 main elements is the minimum, really the minimum. We can focus down in case with some plate is not necessarily the case. And then all the business happens obviously in the end station, which is our TARDIS chamber here at the end time. So how a typical coherent diffraction experiment looks like? Well, you have your diffractometer. It means that you can open under control with angles your samples and detector. This is actually a real signal that was collected on our detector in the early days. You have at a certain moment an aperture that defines, if anything, or filters out the coherent fraction of the beam, at least you. And then if you have everything is perfect, so everything is infinitely distant, infinitely whatever you want, right? You have a Dirac delta essentially on your detector, right? Even if the order in your sample is infinitely extended, right? So infinitely correlated. In reality, obviously, we know that this is not the case. There are instrumental broadening and even sample broadening. So instrumental broadening should be, let's say, that the least limiting one, but anyway, they broaden a little bit, and instead of a theoretical Dirac delta, you have a Gaussian or whatever on your beam. Then you find a correlation in your sample. You see on the reciprocal lattice an extension, right? Because they are Fourier transform one or the other. If you have a coherent illumination, you see speckles, as we saw. And actually, as we said, there is always an intrinsic time structure in your experiment. you can collect multiple images and have a time evolution in case something is varying. If the source beam length, sample position, and detector is fixed, and you see a time variation in your signal, it may be that you have something going on in the electronic ordering of your sample. So we have collected electronic state ordering, and we can access this. And the correlation is sufficient. We plug in coherence, and we can arrange. We can see their arrangement in space and time, right? In homogeneities and dynamics. So, given that it was just supposed to be very general, I just put up a number of examples. It's essentially I hoped in a wow effect, but again, it didn't come anyway. There are a number of things that we studied over time. There are some dates, and you say it. You can see things that are static and things that are dynamic, things that are rotating, things that are almost Fourier transform by eyes, things that are reconstructed. XPCS is in the center. Everything else is imaging. What is really the important part here? But we have sensitivity to electronic inhomogeneity and domain pattern. With quantitative length scale information through imaging and reconstruction. So the space, we can say something. We have access to collective dynamics through XPCS. And again, with quantitative time scales about the time, we can say something, provide everything else is okay, right? As I said. So coherence information, we have to understand and we have to remember is always an integral, right? So it brings down everything, right? As I said, from source to detector. So we need to be careful. Sometimes we manage to do it, even for a long time enough to study very slow processes with time scales of hours. And our upper window at the moment is determined by the detector, which is 100 Hz, just to give you an idea of what we can, the range of time first that we can experience. There are obviously some limitations, exactly the one that I cited are a few of them. The fact that elastic and inelastic are mixed, right? The fact that we are partially coherent. So we are limited by strength of signal in general. There are resolution, stability in the Ewald sphere. In soft is particularly challenging to have anything that populates the Ewald sphere, as you know, because the momentum that you can exchange is very limited. So all things that you have to take into account. But if everything is okay, coherence offers essentially a unique point of view on the problems of electronic behavior in materials. We went a little bit further down the road. That's the reason why I don't insist on cases that you can find in literature, also those you can. But these, I believe, are the parts that are mostly representative of the work done with coherence. So when you illuminate a target and you have a coherent beam, you may discover that you see directly in full field, as it is the case here, things that were not possible to be seen before. What you see here is, in this case, is a multiferroid sample on a magnetic reflection, the 001, at a temperature that is well below its magnetic transition. What is represented in the 4 panels here is exactly the same experiment repeated 4 times after having brought the sample above the transition temperature. So you warm up, cool down, take a measurement. Warm up, cool down, take a measurement, and so on. It's called a return point memory, more or less, or something equivalent. And it shows that there is this wiggly line, black line that you may see here, right? Very well, that is extended over the sample surface. It should be 1 micron, if I remember right, or roughly, maybe whatever. And there are some defects of the sample that are reproduced identical in all the pictures, just because they are linked with the lattice. They have dislocation, even scratches on the surface and whatever. Instead, these lines here are modified each time. Sometimes they are linked to some of the defects, like in this case, and sometimes they are not, because sometimes magnetic domains pin and sometimes they don't, or they pin in a different way. Long story short, these are indeed antiferromagnetic domains. And this is one of the very few techniques, if not the only one, that can allow to visualize those kind of domains, the antiphase domains, in magnetic materials. Obviously, there's a lot of interest in terms of advanced application for electronics, because you can use antiferromagnetism instead of ferromagnetism, as you don't have the energy related with the residual magnetization, and they move faster. And so you can think about doing important things. You need to visualize them to understand if they do what they want or not, or which kind of defects they are sensitive and pinning to or not, and if your sample had them or not. Obviously, stitching, you can create gigantic images. This is, if I remember right, is 2 millimeters by 2 millimeters. So it's something that is really macroscopic effectively, right? It's obviously not very practical. It has been a long exercise by Mingyu Kim, but you can do it. And then you can extract, for example, all the topography of your domains and so on and so forth. But you can do way more. You take another magnetoelectric and that has two competing magnetic phases, and you go across the interesting region where they start to beat one with the other. You go on the reflection that is, for example, the yellow phase here, and you see that by cooling down, you start to see, sorry, it's the blue one, not the yellow. So it's, you start to see that the appearance of the same magnetic domains that we were looking at in the previous case in a slightly different compound. And you see that the topology is completely different, right? You see, you can now, if you want, process the images and try to understand how they grow, how they are born, right? How they germinate, how they grow, how they evolve. For example, what is the relationship between the local curvature and the area of the domains, and all relevant parameters that otherwise would be essentially not accessible. So we understand, right? We have space and time. We saw it already in the previous general slide with many cases. But I wanted to show you that we can raster scan, we can fulfill, we can even reconstruct, and we have time in the dynamics that is coming from the XPCS analysis in whatever form you want to do it. Again, there's much more, because obviously now that you have the possibility of seeing what you're doing, for example, in this case, it's by the aid of zone plate illumination, so that we increase the amount of flux that is focused on a smaller area of the sample, 10 micron now it's indicated finally. You see that we are looking at a stable temperature and seeing how the sample behaves. In this case, obviously, you have a dynamical equilibrium, and the sample is exploring various configurations that are allowed and practically equivalent in energy. Right? And you will see that this is the area of interest. By the way, here we are. It's starting to change quite a lot, and it's reported here, right, in its evolution. So you can see how effectively some of the domains are germinating or changing. And compared to before, we are not sweeping the temperature anymore, but we are fixed here, right, at the border between the zones. So where effectively some frustration, because multiple options for realizing magnetic structure are allowed in the system. Then you can use XPCS approach and see that this is intercepted indeed if you analyze this part of the image. And actually, if you extend the time enough, you will see that the sample does a lot out of what is allowed to do. So obviously, we are talking about space and time, but a little bit of space or time somehow, in the sense that if you want beautiful contrast, you want to acquire longer, so your frequency of acquisition of images has to be extended in time. If you want to be very fast, you have to compromise with the amount of details that you can extract from your images, because the number of photons that are arriving on the sample is limited. And so some details will be lost, and also signal to noise in general is worse. Right? That's the point. Apart for general concepts, going down to the quantum mechanics, as we heard indeed from Antoine as well, the process that we all know is called blind averaging. You take a set of data, you squeeze everything, right? Averaging everything, and you increase signal to noise. It's true, but in this way, you destroy part of the temporal information. You actually are extracting only the part that is constantly summing up, the part that is not fluctuating, if you prefer. Yeah, the rest goes into the noise, right? Instead, if we were able to knowing the instantaneous state that our system is populating, even without having the pool of the intensity to resolve all the detail, it would be great. But in this case, we would need a selective average, right? And so it's a little bit of a difficult mindset that we have to enter to try to understand what we are talking about. However, to try to explain it better, it's an idea that came on the beamline a long time ago. And then finally, we got the opportunity of working with people that were experts of holography. And so we use this perpendicular magnetization multi-layer, artificial multi-layer, that are magnetic at room temperature, so it's an easy system in this sense. And they prepare fantastic samples with very beautiful holography masks. And as you know, everything becomes very easy, because by propagating the wave that is impinging on the sample, essentially what comes out can be directly Fourier transformed to reproduce what is inside the sample. Essentially, the complexity of the phase problem of the diffraction comes in the complexity of preparing a mask for a sample. But if you know how to do it, you have the opportunity of Fourier transforming back everything. And how does it work? Being an orthogonal magnetization sample, it requires XMCD to be sensitive to the spin component, right? That is orthogonal aligned with the beam. plenty of XMCD effect in these samples. So you acquire circular plus and circular minus, the two helicities of the light and the two diffractograms, so to the two allograms, you make the difference, you Fourier transform, and you discover that you have exactly contrast in the image that comes back that encodes the magnetic state, either up and down or down and up, whatever, into your sample. And you see very well here reproduce again the problem of the space or time. You want to, if everything is static, right, you pull down your system enough that everything is static at the limit if you can, you want to acquire as long as possible to try to get the best contrast possible, top picture, 2 seconds. You want also to understand if everything is static or not, so you may want to squeeze down the time as much as possible, but you have to compromise in the quality of the image. Can we do better? Yes, we can. Actually, this was a long acquisition that I asked to be taken overnight when people were going to sleep. It's 5 hours of acquisition. And it shows that the sample was almost at equilibrium, but still relaxing a little bit. It was brought relatively close to the transition temperature. And so obviously the magnetic domains were experiencing and trying to move around a little bit around, right? For what was allowed. Actually, at room temperature, plenty of energy compared to the energy of the domains. And so obviously then you see again the same problem. Blind averaging means area with less contrast, because in reality it's there where the motion is happening, right? Or you want to be fast, you destroy your image because you don't have it. So again, selective average. If we were able to know when the sample is in one state or in another, even if we were not capable of labeling the states, but knowing where it changes, then we would collect selectively the image in one bin or in another and finally transform. It's exactly what we did. We defined a suitable matrix. I don't have time, actually, probably I'm already late, but long story short, we can have information on space and time of electronic behavior. And the whole of the trick is to define the right metrics and having a computer program that tries to understand when the sample is in a state or changes something. And given that the images are time-stamped, you don't only know at the end which states that you can reconstruct with the signal to noise that is allowed by the number of images that end in the specific bin, but you see that they are similar but all different essentially, and there are most of them completely resolved, not all. You don't know only which states were populated, but given that the images are time-stamped, you know also when they were populated and which state brought to which state and not to each other. So it's a new completely way of accessing microscopic information in this sense, in particular for phase transition. And it's this coherent correlation imaging that we did as an effort, generating finally this tree, which is called the connectivity tree. As I said, which state is occupied, connected to which ones, which are the somehow hinges to move from one subset to another, which are similar and not. It can be generalized, obviously. Any source with sufficient coherence would generate the same. If you have a full field, fantastic, you can do it. We use the correlation-based, XPCS-based metrics, but it can be different. And imagine how powerful and important would be for pump and probe experiments, where you pump and you don't know if you end up in the same state. You assume that this is the case, but with this technique, you may understand if you are in the same state or not, right? Sorting out different states and potentially extracting more information out at the cost of a signal to noise, obviously, but also more reliable and with more details, not having to compromise necessary space and time. Obviously, there are limitations as any other techniques, and it's particularly important if there is recurrence of states. So if you have a continuous evolution from minus infinite to plus infinite, the technique will tell you just there's nothing that is actually accumulating in the same bin. It's important to know, however. Sometimes, actually, we are surprisingly enough, most of the time, we have some kind of recurrence, and so it's actually effective. Okay, we had, let's say, various kind of contributions that we saw across this talk over the last 10 years of operation at CSX with partially coherent beam in the soft X-rays. Apart for direct Fourier transform in diluted case, the work done with Alex Frañó, we have also full field imaging, antiferromagnetic domain, unique because of the information that we extract and the large field of view that is allowed. We have the space and time in mixing, this concept that I was trying to draw at the beginning of the talk. And what I would love to say is that the original concept of squeezing down the electron beam and increasing the coherence that was only in space for obvious reasons has actually exceeded the expectations, because starting from something that was supposed to give better details in space and maybe better details in time, ended up being something completely new and different with space and time. Connectivity 3, that to my knowledge is about the only time that I saw anything like this coming out of an experiment. So which conclusion can we draw? But coherent soft X-ray, resonant elastic X-ray scattering, we can see interacting electrons. Actually, we are relatively strongly interacting, but we can see buried interfaces. So there are also very important applications, obviously. Adding coherence, we can access mesoscale imaging, even full field. And we have, obviously, imaging in the sense of space and collective dynamics for time. But we also prove the transformative approach of space and time. We are excellent overall in microspectral diffraction imaging, tour of electrons in strongly correlated electron system in particular. And our photons are eager of new scientific challenges. So if you have questions, just reach me out. More than happy to discuss. And I conclude with the perspectives, right? Future looks even brighter, fourth generation sources. Now it's you guys. But in reality, I believe that the paradigm change is required to exploit them completely, right? The stability, the control, the multimodal are all keywords that are fundamental, absolutely. But we have to change the mindset by which we think about all of them probably. And it's like the equivalent of saying the difference between extrinsic, intrinsic, mixing, and demixing, right? If you understood something of the seminar, I believe you understand what I mean. Is the OM the next degrees of freedom to exploit in this sense of mixing the mixing? Maybe. Opportunities for simulation and retrievals. Automation will be the key. Artificial intelligence and machine learning is the natural playground, but I would not hear big data. It's not big data, it's new metrics. It's the way in which we look at the data. It's not their size. Size is a scalpel problem. Instead, we want to cut through in a different way. We use the XPCS because it came to our mind that this matrix was ready and it could be effectively used as a matrix when up to now people use it for a different thing. It worked. But this is only what was available there. We took it and we plugged it in. In reality, there are certainly new metrics that are way better to discuss and describe and reproduce the physics that is inside our measure, for sure. In this sense, also new approaches, dichotomo, full field depth, so three-dimensional enclosure of information and how to, again, look at it, extract it, and I guess the Xiaojing will tell us about it. Energy control, scatter beam, we don't do anything because either it's very, very ineffective or destroys or affects heavily coherence. That's the next experimental step that I would like to see put in place. And actually tender, right? Everything is pushing. When Antoine says we are not fully coherent over there, we always have to say at which energy, right? Because at 150 kiloelectron volt, anyway. So tender X-rays will be the newest soft X-rays in the sense that we have been partially coherent now. We will be fully coherent in soft X-rays, but not really in tender yet, or with the same limitation we're experiencing now in soft. There's a lot of scientific cases that are just there waiting for us. And what we did in soft is just around the corner in tender. With actually topological, typically, right? There's a number of topological systems, a number of L-scalar S-based physics that is very interesting to be investigated with a new approach, a new, as I said, future sources. Give me an X-ray laser, which are not the current FELs. Okay, this is my message. Thank you very much. Okay, questions?
It was a wonderful talk. I just want to know what is the future application as X-ray lasers are not yet there, like for the biological interface, like charge transfer or electron transfer, especially for photosystem systems.
So we purposely stay far from soft matter because it is difficult to deal with the intrinsic problem, and I'm absolutely not an expert in it. I suspect that in that case, the FEL may be in a better place just because you fire, destroy, and forget somehow. Maybe not. So in general, it will be tough because of the strong, especially if you're resonant. We tried, obviously, imagine MOF samples, right? It's the first thing that I tried as soon as I moved to a soft beam because I said, fantastic. They look like a crystal for our X-rays, and they have an infinite amount of parameters we can control, degrees of freedom we can play, right? And we go through the lattice, so it's a strong coupling, and we don't have to. Fantastic. There is no one that survives resonances. Because when you target resonances, you are hammering on the same electrons that are keeping everything together. So it is very tough. If you have samples that are surviving this treatment, let's say, it's certainly extremely interesting. It is realistically very difficult to have any. This doesn't mean that we don't have to keep trying and come up with good ideas, maybe to extract the best out of our data that maybe we don't understand completely yet. This is what I would say.
Any other question? Okay.
Yeah, great talk. Just follow up on that. So you mentioned there's a space and time. There's a dilemma there. So what is there a metric to quantify the amount of the time resolution you get with the tolerance of the radiation that you have?
Yeah, sure. In the paper, actually, this is a full work of our collaborators, extremely, very, very good. They spent a lot of time in trying to show the limitations and the coupling between what you do in time, what you do on space, the dose and everything, right? Somehow at least. So obviously you always have the same problem. You are dealing with a signal, and so you have a signal to noise in any sense, right? So you have an unfixed amount of photons if you prefer, and you have to decide how to distribute them. But let's say that this method that we invented or noticed essentially is a way of extracting the best possible within those limits, we believe, right? And then you may obviously deciding depending on how short you can expose per image, you can give privilege to time resolution as opposite to space resolution. If you compromise a little bit on the fundamental unit that you have as clock in your system, you may get a little bit better, but it depends really on the signal to noise, on the signal itself, on many multiple characteristics. So it's difficult to say immediately out of the blue. This is also the reason why there will be always need of experiments, because you can simulate everything except what you don't think about. And typically samples in nature try to put stones in your path, right? And say, and this is where it comes from. Oh. And now you have to deal with it, and you have to find another procedure to try to see if what you think or you want to model out of is effectively realized or not.
All right, let's thank Claudio again.